Today we are going to derive the value of electric potential due to a point charge. The value of electric potential due to a point charge, that is V due to a point charge. So as we discussed last days, in order to determine the electric potential at a point in an electric field, we first find out the total amount of work done in bringing the test charge from infinity to that point and then divide it by the magnitude of the test charge. This ratio will give out the potential at the point of observation. Now let us draw a uniform electric field. A uniform electric field intensity line can be drawn from a plus Q charge, correct? So consider a point charge. This point charge is our source charge plus Q. So consider this point charge plus Q and that is placed at a point O. So electric field intensity definitely I can draw from this plus Q charge. So where will be the direction of this plus Q charge? It is always directing radially outwards from this plus Q source charge, correct? So from plus Q, the electric field intensity line I am drawing here and I am marking it as E vector. The next step is a point P is taken at a distance R apart from the source charge at which the electric potential is to be determined. So from the plus Q charge, from the source charge, I am marking a point P here. Okay, I am marking a point P here which is at a distance. How much? It is at a distance R from the plus Q charge. Now I am taking a point that is A in this uniform electric field intensity line. A point A is being taken in this uniform electricity line, and in this point I will be placing a Q naught test charge also. So from the source charge, that is from plus Q charge, the distance can be taken as X. So the point A is at a distance X from the plus Q charge, from the source charge, and at the point A I am supposed to place a Q naught test charge also. So what I will place in this A point? Q naught test charge. So definitely this plus Q and the plus Q naught charge both will be under electrostatic force and under electrostatic force of repulsion. Since both the charges Q and Q naught are positive in nature, they will definitely experience a Coulomb force of repulsion or electrostatic force of repulsion. That means their electrostatic intensity or force direction will be always going outwards. They will not attract each other, either they will repel each other. So I can write the value of electrostatic force here, Coulomb's using the Coulomb's law of electrostatic force on this test charge Q naught. That value will be definitely force F will be equal to 1 by 4 pi epsilon 0 into two charges are there. So Q into Q naught divided by distance square. What is the distance between these two charges? That is from plus Q to Q naught, the distance is marked as X. So definitely force value will be like this. F equals 1 by 4 pi epsilon 0 Q naught divided by X square. This will be the value of force of repulsion acting on this test charge Q naught. I have written the concept of work also in this paper. So definitely an amount of work, a small amount of work should be done in bringing the test charge Q naught against the electrostatic field from the point A to a point B. So a dW work should be done in bringing the test charge Q naught from the point A to the point B or somewhere else in that electrostatic field line. So how much is that work value? dW will be equal to force dot dx. How much is the small displacement value? So the small amount of work will be equal to force into small displacement value dx. Dx is the distance between point A and point B. From the point A, the test charge Q naught should go to the point B. So the distance between the small displacement between A and B is termed as dx. So the total amount of work done in bringing that test charge Q naught to that point B will be given by force into dx. Why this minus came? Because the electrostatic field intensity line is being drawn in that direction from left to right, but I have to move this test charge Q naught from A to B, that is opposite to the direction of electrostatic field intensity. So definitely both these directions are opposite, that's why I have given this minus in this equation. So in order to find out the total amount of work done, dW should be integrated to get the total work. So dW, when I am integrating, I will get the capital W total work done. Total work done will be equal to integral from infinity to the point R. That means the lower limit is infinity. I have to get the test charge from infinity to my point, that is at R. From infinity to R, how much work should be done? Work done, W will be equal to integral from infinity to R minus f dx. That will be equal to W equals minus of integral infinity to R f dx. The value of force is being already written up. So force value was equal to 1 by 4 pi epsilon 0 q naught by x square. If you substitute there, minus of integral infinity to R 1 by 4 pi epsilon 0 q naught by x square into dx. This 1 by 4 pi epsilon 0 q naught by x square, the value is electrostatic force of repulsion, and definitely one dx values remain. So that one also I have written minus of 1 by 4 pi epsilon 0 q naught by x square into dx. When I am taking it out of the integral sign, the constants I am taking out of the integral sign, what I will get? Minus q naught by 4 pi epsilon 0. So the terms remaining are integral from infinity to R 1 by x square dx. You know the value of 1 by x square dx. What is the value of integral 1 by x square dx? You can use the common identity x raised to n dx. Here it will be, when x square comes to numerator, it will turn to x raised to minus 2 dx. That will be x raised to minus 2 plus 1 by minus 2 plus 1. So definitely the answer will be like this: q naught by 4 pi epsilon 0 from integral infinity to R x raised to minus 2 dx. X raised to n dx is x raised to n plus 1 by n plus 1. Answer will be minus 2 plus 1 by minus 2 plus 1. Answer will be x raised to minus 1 by minus 1 dx. Instead of x raised to minus 1 by minus 1, I can write like this: minus of x raised to minus 1. When x raised to minus 1 power is coming, that means x can be taken to denominator side. So minus of 1 by x will be the answer for integral of x raised to minus 2 dx. So what will be the final answer for work done? Work done, W will be equal to minus q into q naught by 4 pi epsilon 0 into, instead of integral x raised to minus 2 dx, we got the answer like this: minus 1 by x. So the limits are also there from infinity to R also. So after this step, we have to apply the limits also, that is upper limit as well as lower limit. So work done will be equal to minus q naught by 4 pi epsilon 0 into, we have to apply the limits, upper limit minus lower limit. Instead of this x, you have to apply upper limit R first, then minus lower limit, that is infinity second. After the substitution, I will get like this: upper limit minus lower limit, 1 by R minus 1 by infinity. But you know the identity like this: 1 by infinity is nothing but it is 0. So only 1 by R will be left out. So what will be the final answer for work? Work W will be equal to q into q naught by 4 pi epsilon 0 into 1 by R. Thus, because of this derivation, we could formulate the equation for work done. Now our ultimate aim is not to calculate the amount of work done. Instead, it is to calculate the potential at a point due to a point charge. So potential equation is V equals work divided by Q naught. We have studied it in the previous day. What is the equation for, what is the relation between electric potential and work done? That is, V will be equal to work done divided by the test charge Q naught. Work divided by Q naught. Work equation already it is written up. So work q naught divided by 4 pi epsilon 0 into 1 by R whole divided by Q naught. Q naught and Q naught, definitely it will cancel each other. So what is the value left? That is the final answer. The potential V at a point due to a point charge is given by V equals 1 by 4 pi epsilon 0 Q by R. This is the final answer for electric potential due to a point charge. 1 by 4 pi epsilon 0 Q by R is the value of electric potential. So when we compare the equations of electric potential with the electric field intensity and electrostatic force of repulsion and attraction, we can formulate an inference like this. All the previous equations were obeying inverse square laws, that is 1 by R square, force as well as electric field intensity. But now the electric potential is obeying only inverse law, that is 1 by R. V equals V or proportional to 1 by R. But force was equal to 1 by 4 pi epsilon 0 Q1 Q2 by R square. Electric field intensity equation was like this: 1 by 4 pi epsilon 0 Q by R square. But electric potential is, it is V proportional to 1 by R, inverse law only. So this is the major difference between electric field intensity and electric potential. One was obeying inverse square law, one is obeying inverse law, 1 by R only. So students, write these notes in your notebook. Thank you.